Okay, gang. Method. Well, I don't know what happened. 6610. The purpose of this video is planned comparisons, but I think it's a really good time to kind of step back a little bit and talk about some things. I've noticed from the feedback from some of the exams and the homework, I'm not sure that it's completely clear about the assumption. So I want to look at some stuff first before getting into the planned comparisons. Actually, we call it planned contrast, but we'll talk about that in just a second. So, guys, in statistics, we often ask, is a test robust? And we often hear people in statistics ask similar questions. And in this video, what I want to do is I want to revisit ANOVA. And essentially, I want to ask, is ANOVA robust? Now, I think the very first thing that we've got to do is we've got to come up with a working definition of what it means to be robust. So at the end of the day, when I think of robust, we're essentially asking ourselves the question, if we break the assumptions of ANOVA. And guys, we should know up by now that the assumptions of ANOVA are normality, equal variances, and independence. So if we break the assumptions of normality, then will the F ratio still be accurate? Now, breaking this down a little bit further, the first issue that we need to talk about when there's a threat to the F statistic in ANOVA, we need to ask ourselves, and let's just go ahead and just say this is issue number one. It should be pretty clear where I'm headed with this. Does the F statistic control the type 1 error rate? Another way of saying this, let me scoot up a little bit. Is our test result statistically significant when there are no differences? So, being robust. I'll tell you what. Let me reset the. Okay, trying to get things where you guys can see it. Okay, all right. That looks a little bit better. So, guys, at the end of the day, what I want you to think about is the underlying probability distribution. For the ANOVA deals with the number of groups minus one and our total sample size minus the number of groups. But when we violate an assumption, there's a possibility that the underlying probability distribution isn't what we think it is. So you could easily see that if we think that we have a 0.05 error rate, and the distribution that we're truly drawing from because of the violation of assumptions um, differs from that, then we have issues on not only the type 1, but the type 2 error rate. Okay, so speaking of, issue number 2. Does the F have enough power? So does the F statistic have enough power to detect differences when they exist? And guys, remember that we're all pretty good at this by now. That this clearly is related also to the type 2 error rate, which is beta. Now, guys, we talked about again in ANOVA that we have 3 assumptions. And what I want to do is just run through with you what the research actually says. Field has a textbook that I think really kind of summarizes this really nicely. And Tabishnik and Fidel, or Fiddle, I never did figure out how that she pronounces her name. But they do an excellent job of this too. So what they found in terms of normality is that back in 1972, Glass reviewed the literature and found that when the normality is violated, that the F controls the type 1 error rate. So there's not a drastic difference between what we think we're getting and what actually the truth is. And what we can say there, I guess at the end of the day, is that skewed distributions have little effect on error rate and power. Now, guys, the main reason I'm presenting this is just based on feedback that I've got from you guys, and it's completely normal or completely reasonable and understandable that based on the things I've taught you before, if we have normality assumption that's violated, it's so easy to want to maybe throw the baby out the bathwater there and just jump into a non-parametric test. So the reason I'm making this point is twofold: to kind of correct some of the things that I'm afraid I haven't made clear up to this point, and secondly to set the foundation for some things, the play and contrast that I want to do. There was another study that came in, and I forget this person's name, first name, Box. It was actually a female statistician. Questioned the results in terms of certain types of skewness. So up until Box came on, looked at just skewed distributions in general, and it seemed like they had very little effect on the error rate and power when conducting ANOVA. Well, Box put her attention into what's called kurtosis. Now, kurtosis is a violation of normality, and it's kind of I don't know how pointy that a distribution is. So there's 2 types of kurtosis, one that we call let's see, that should be Kurtic. And in this place, it's kind of a positive kurtosis, and we have a situation where it's too pointy. So it violates the normality assumption based on kind of the pointiness. The platy Kurtic, as you would expect, isn't pointy enough. So too much point, not enough point. And we can, I'll tell you what, guys, let me get this out of the sun. I think this is messing with the clarity. And what she found is that in too much point, we found that, or they found, I didn't find it, is the power is too low, and in this situation here, the power is too high. Now, sometime later, researcher Lunny came on board. This was, I don't remember, probably around the mid-70s, I think, and found out that in a very specific case where our dependent variable is either 0 or 1, and our sample sizes were all equal, and the degrees of freedom were greater than 20. And a further thing, the smallest response category contained at least 20% of the observations. So all the times of these restrictions, if you will, so the smallest response contained at least 20% of the observations. You had a situation where your ANOVA results were robust. Donaldson came around, I think, a little bit after that. I'm not really sure when. Stevenson at the University of Cincinnati, I'm pretty sure is studied. Oh, I'm not pretty sure. I know he has. And at the end of the day, when you actually look at all the literature, you can pretty much conclude that when group sizes are equal, power, well, let's say errors and power are mostly unaffected. So summarizing, we might say that the F statistic is quite robust to violations of normality when sample sizes are equal. Now, guys, you're going to see a common theme here, and the common theme is controlled experiments where you can actually control the sample sizes have extreme benefit. And I will kind of add as just going to add on here. I don't find the research to be really clear when we have sample sizes that aren't equal. And maybe it's out there, but I'm just not tapping into it. That ANOVA reacts unpredictably. when we're in the presence of non-normality. So let's move into the to the second assumption for ANOVA. What happens with equal variances? So we're trying to run an ANOVA, or remember the things that we're looking at in this class are really a result of the ANOVA family. We started, basic with t-test and things, independent, dependent sample, and even a one sample t-test. But then we moved into ANOVA, and then we went to two-way ANOVA. I hope to illustrate a three-way ANOVA just to show you the madness that happens there. We got ANCOVA, still in the ANOVA family. We have a repeated measures ANOVA. And I guess next week we'll get into MANOVA, which is the multiple analysis of variance. Well, guys, I'm not going to go through all of the literature, but when equal variance assumption is not met, and we have equal sample sizes, it turns out that ANOVA is fairly robust. And again, a lot of literature out there on that. Now, what happens when the sample sizes aren't equal? Well, it's not robust. And kind of wacky stuff actually begins to happen. It actually shows that when the larger groups, so let's say that there were 50 in N1, 45 in N2, and then it comes down to 30 in N3, whatever it may be. So when the larger group, which in this case would be N1, has the larger variance, it turns out that the ending result is problematic, and it turns out that the F ratio will be too low. On the other hand, when the groups with larger variances have the smaller sample sizes, our F ratio gets too aggressive. In other words, it starts finding differences when they don't exist. So it inflates the F ratio. Speaking of equal variances, what seems to be the kind of the universal solution to if equal variances is actually violated, what seems to be the the pill that takes care of that? Well, let's have equal sample sizes. Guys, let's come into the last one. What happens when we violate independence? Well, first of all, this is by far the most critical. Let me get my pencil up here, okay? And it's so serious, I'm going to put all that in capital letters. Now, guys, remember, independence is just where our observations across groups are highly correlated. So there was a study done about 1990 or so that I thought was kind of interesting. And what they did, they set alpha at the standard 0.05, and this, of course, would be where independence was not violated. And they violated independence and found that the true alpha level was about 0.75. And let's put approximate. It may have been 0.72, but I remember it was about 0.75. And what they did here, it seems like it was, well, I can't remember. But what they did here is they set up 3 groups, and they made these things correlated, which means independence was violated. And it seems like the correlation between the groups was pretty modest. It wasn't like 0.9 but it seems like the correlation coefficient was kind of a modest correlation at 0.5, and they had the sample size equal to 10. And it turned out that the alpha value was severely inflated. And instead of testing at 0.05, they were actually testing at approximately 0.75. Now, if you think, let's just assume it was 0.75, and I believe it was just a little bit below that. But back to one of the earlier diagrams that we gave, a really good way of thinking about type 1 and type 2 errors is to look at this table, where H sub O is either that the value is true, or the statement in the null hypothesis is true or false. And on this part we have the decision of reject or fail to reject. Well, guys, these 2 boxes right here clearly specify and define the errors that we encounter in statistics. If you think you're testing at 0.05 and you're actually testing above 0.70, then your potential to reject a true null is clearly inflated. Now, guys, the shading has moved on me, and it's not cool because it's not. It's kind of messing with what you guys can see. The challenges of teaching online. It's funny when you teach online. I've said it over and over and over. I think anybody who ever takes a class online needs to have taught a class online before they take it, because there certainly are certain challenges. Now, guys, moving forward, let's be pragmatic here. And what if our assumptions are violated? As long as our sample sizes are equal and the violation isn't independence, I think we have reason to support moving on with a standard ANOVA analysis, or if we're in a repeated measures ANOVA or an ANCOVA, whatever it may be, to go ahead with the basic violations. Now, once we get into other, like repeated measures, sphericity, then those are not violations that I'm addressing in this video. But guys, if things are violated, there are other things we can look at. Number one, which I think is a really, really, really cool technique, and I hope I get to teach that to you either this semester or next, called bootstrapping. There's another thing we can look at called trimmed means. And at the end of the day, if you want something much more straightforward, remember the non-parametric design that we looked at earlier in the class. And of course, for the ANOVA, a drastic violation in either normality and or equal variances, and your sample sizes aren't equal, well, we've got the tool for you. Okay. Now, let me try to get this over here where you guys can get it out of the way of the... Got to tell you, the girls and Tanya are home today, so I'm kind of out of my element here because I got to blame it on something. All right. So let's go on and examine in a little bit more detail ANOVA. Really not examine. Let's re-examine. Let's review. And I want you to appreciate that everything we're saying here is generalizable. But back to the ANOVA, the F statistic looks at the ratio of certain variances. And what it does, it takes the sum of the squares for the group divided by the degrees of freedom for the group and looks at the sum of squares for the error divided by the degrees of freedom for the error. And of course, this gives us the ratio of the mean square for our group term divided by the mean square for the error term. And once we run our model, the more variation that we have that we can explain in the group term, our F statistic is raises, p-value goes down, so we get more evidence against the null hypothesis. So in other words, guys, if the model that we fit to the data, which is our explained variation, okay, accounts for more variation than the extraneous factors, which is the unexplained variation, then we're clearly going to have an F ratio that's greater than 1. And if there's a significant difference between the explained variation and the unexplained variation, we get an F statistic that's becomes statistically significant. So guys, again, what does that tell us? Setting the stage for bigger, better stuff. If we're testing group means between K means, between K groups, the null hypothesis would clearly be that the group means are the same, and the at least one pair of means is different. Now, I'm trying to make bigger points here in terms of the connection between ANOVA and regression, and I've done this in previous videos. But if you think about the relationship between ANOVA and regression, there's obviously a lot of similarities. If we run an ANOVA for regression, as I hope you remember from 5500, and we have K predictors, our null hypothesis is that all of the parameter coefficients are equal to 0. The alternative is that at least one of these is not equal to 0. Now, what did we do back in 5500? I think some of you would really like to forget that class, but I'm not going to let you. So if we go back to 5500, what was the implications of statistical significance? So we got an F statistic that, whatever. Our p-value is less than 0.01, for example, meaning that we would reject the null. and conclude that at least one of the b sub i's is not equal to 0. Well, what would we do next? Well, what we would do next is we would, in multiple regression, our next step would be to test each of the beta coefficients. Right? And with each one of these beta coefficients, we could create a test statistic and a p-value, and ultimately we could do a 95% confidence interval. So if we were trying to predict first-year college GPA of a high school student from their high school GPA, their SAT score, their ACT score, and different set of variables, if our ANOVA is statistically significant, we're indicating that at least one of those is a statistically significant predictor of first-year GPA. These kind of planned, to make a segue here, these planned comparisons, if you will, to go ahead and look at each one individually would be the next step. Well, in ANOVA and other tests, we got to be really careful. And the reason we have to be careful is that these straightforward multiple comparisons that we do so easily back in regression inflate the type 1 error rate. Now, the classic case of this would be to look at 4 groups and we reject the null and we compare mu1, mu2, mu1, mu3, mu1, mu4, and so on and so forth. Well, guys, if we're accepting, for lack of a better word, well, that's exactly what we're doing. If we're accepting a probability of a type 1 error at 0.05 for each one of these comparisons, it should make tons of sense to you by now that if we conduct multiple tests that we're going to inflate that. Well, we've got to have some way to actually come in and control for that. Yet still make the multiple comparisons. All right, gang. That's where we get into post and ANOVA that's statistically significant, then what do we do? Well, there's actually 2 ways. And the first way that you are very aware of, and it's the easiest, is called a post-hoc analysis. And names that should pop in your head immediately are Tukey, Chaffee, Bonferroni. And what a post-hoc does is it compares every group. Advantage, easy to do, and literally conducted post the experiment. It's not something that we have to plan for. We run our analysis. We typically, enter the appropriate code in R, and we get all these multiple comparisons where these people like Bonferroni, Chaffee, Tukey, and so on and so forth they've actually controlled for the type 1 error rate. The second way to do this is to do what's called planned comparisons. And you can add a big old fancy term to your repertoire now in statistics. We call these things planned contrast. Now, the advantages, I should say the disadvantages, I think they're a little more difficult. So they're a little bit more challenging. Another thing to keep in mind is they must be planned before collecting your data. So there's a little bit of data manipulation, not in terms of manipulating data to where we get something other than, where we create bias, but these are just called planned contrasts because they literally are. Now, I'm not sure what time it is, but I've got an appointment. What time is it? 2:15. Okay. All right. Well, I'll tell you what. I'm gonna end this video because I've got a doctor's appointment here in just a few minutes, and I've got driving time. So that's going to be the end of this video, guys. What I'm going to do next is I'm going to demonstrate via a video where we look at let's say some kind of experimental versus control setting, and in the simplest way when we look at experimental versus control, sets up the kind of the classic planned comparison discussion. So guys, that's all I got. We'll get on this more in the next